Hello, everyone. Welcome to this training session about Introduction to Machine Learning with AWS SageMaker. And my name is Sun Chang. I'm working as a senior data scientist in Grab, and I'm going to be your instructor today. So for this course, we are going to talk about the basic concepts about machine learning. And the takeaways are going to be, you are going to learn how to solve regression and classification problems via linear examples. But also you should be able to train, select, validate, and evaluate your linear models. As well, you will be able to make use of AWS SageMaker to train, deploy your model, and make predictions. Okay. And some prerequisite for this course, I presume that you have already got enough knowledge about statistics, expected value, variance, and normal distributions. Also, for coding part, I think you have gone through the sessions about Python and be familiar with this development environment about Jupyter Lab, and also some famous Python packages, pandas and numpy. Also, you have gone through the AWS training session about the AWS console and S3. Okay, so let's begin with the introduction. Okay, so if you have any questions, just type it in the chat. I'll attend it later when the session is end. Okay. So as an introduction to machine learning, please look at this graph. So by contrast to the traditional AI system, machine learning is a kind of system that makes use of a lot of data you collected to train the model first, then use the model you have trained with the data to do predictions or to interact with world. Both the machine learning and the traditional, say, rule-based programming, they are trying to find a hidden relationship behind the data. But machine learning, because the rules behind the data sometimes is not as easy as, say, Newton's rule, F equals to ma, such kind of closed form relationship. So the rules behind the data is going to be difficult to describe. So instead of writing the rules explicitly, we make a guess first. Okay, how these rules will be look like a rough skeleton of this model. Then we use a lot of data together with this kind of skeleton to fit the model. So the model will be able to find the best fit to those data. And this kind of system generator will become a predictive model we have built. Okay, so in this sense, data is a very important key to generate rules, and it decides how predictive your model is. Okay, so the first important concept is what is machine learning different from the traditional programming? Okay. Then there are three main different categories for machine learning. First category is supervised learning. Supervised learning basically means that your data is together with the answer. So you know the desired output. It's supervised. So you are given the answer and you do the training to do predictions. And the main two problems in supervised learning will be classification and regression problems. And most of the problems we are solving today are falling in this category. So in this session, we are also going to focus on supervised learning. But there are two more categories. Okay, by contrast to supervised learning, there is an unsupervised learning. So unsupervised learning means there is no desired output. You just look into the data and and perform some task according to your own metric. Say you want to do some clustering, you are given a lot of data points. You just want to cluster them into different groups. So this is kind of clustering problem or fraud detection. You detect some outliers of this data set. Yeah, this is so-called unsupervised learning. You have no desired output, or we call it annotation. Okay. Then the next, the last category is some kind of very new, and they have gained a lot of attractions. They have gained a lot of attentions, which is reinforcement learning. Probably you have heard about a lot of artificial intelligence system like AlphaGo, which can play Go intelligently with human, and they can beat even human champions. Also, robot control, which is a very dedicated control that make robots act like humans. Okay, so this kind of learning, they have an agent, and they train the agent to interact with environment and watch the results of interaction to learn how to react to each state. So going into details, say supervised learning is like this. This is the model you want to build. It's a brain, okay? And these are the input data, say an image of apple. And together with the image of apple, we are going to annotate it, calling this image apples. Okay, they are apples. So we tell our model that, okay, this kind of image is apple. So next time I input some other images that are similar to this apple, we are trying to predict, this system will predict whether it's an apple or not for it. So this is a very typical supervised learning. Okay, so unsupervised learning, okay, this time we have a mixture of apple, orange, and banana, and we want to tell from either the difference in the image or any kind of metric we define to group apples together, oranges together, and bananas together. So this time we have no annotation tells you, okay, here there are apples, oranges, or bananas. So we separate them using our algorithm. Also, this is so-called clustering problem. And the last one, reinforcement learning, which is a complicated learning system. And usually there will be an environment. Say environment could be the real environment or a game. Okay, a game, say like Go, which is a very well-defined game. And this game is an environment for you to train the agent. So the agent is acting as your system. This system will do some actions, and the environment will give you some rewards. Okay, so the rewards will be given whenever your action will lead to some outcomes. Say, for example, you jump and fell. That means when you train this robot, you know that this kind of jump will lead to fail. So the fail will give you a negative reward. You know that the next time this kind of jump is not allowed. Okay, then you observe the reward. You adjust your behavior next time. And here there is a very interesting video game. Not video game. Interesting video that shows you how the reinforcement learning can be applied. Say this kind of robot control by Boston Dynamics. Okay, they can train the robot to perform those actions that human can do. Just imagine how you learn how to walk during your childhood. Okay, this is actually similar way, actually we can say that reinforcement learning is more similar to how human do the learning process. Okay, they learn by do it again and again. Also, there is another agent, reinforcement learning training, that tells the agent to play Super Mario, which is a very well-known game. Okay, for the first few iterations, they will just stuck there and doing nothing. They don't know what to do, but they know that when they do this, they will it will lead to a die. Okay, when they die, they know that this action is not rewarded well, so they change the action, say maybe move forward or jump. Okay, so every time they play the game, they will learn some cases that they will die. Then as it goes along, finally this agent will be able to realize, okay, this is the best sequence of operations. Okay, move and jump. Whenever you see this small little monster, you have to jump. Okay. Yeah. So this is a concept and applications of reinforcement learning, and it's a lot of fancy products has been done upon that. But as I said, most of the real life, okay, if you are not joining those Boston Dynamics company, you probably will not use the reinforcement learning quite a lot. Supervised learning is the largest category that we are going to deal with. Okay, and here are some known, very well known models for different categories of machine learning model. Say supervised learning, we have linear classifier, naive Bayesian model, support vector machine, decision trees, random forest, and also neural networks. Okay. Unsupervised learning, we have PCA, K-means, DB-scan. These are all some well-known algorithms that helps you to build machine learning models. And for reinforcement learning, you can see there is Q-learning, also lambda. Okay. Okay. So far, even I haven't explored all these models. Okay, because reinforcement learning, as I said, you won't be able to encounter use cases when you really need a reinforcement learning to build a product. Okay, because it's too expensive and too hard to evaluate. For supervised learning, it's the easiest. You can check the output, whether how far away it is the desired output. But for reinforcement learning, you can only train again and again by playing this game, say again and again. And then when you train the model, you have to play the game again to see the score or whether it can beat humans or not. Yeah, this is how the reinforcement learning is doing. Okay. Then we, after knowing the general classification for machine learning, we are going to the general process of building a machine learning, how data scientists build a machine learning model. We start with raw data. Okay, raw data we collect from either our database, from any open source website or any other sources. Okay, we collect by API calls or anything. These raw data usually comes in with various forms like videos, sound, images, text messages, and so on. So before we can make it a model, we have to pre-process those raw data, changing the form, changing all the data form into a structured data. The structured data, what I mean is a tabular data with all numbers, because machine can only recognize numbers. So we have to do a series of pre-processing in order to make unstructured data to structured data, and use the structured data to build our machine learning model. Choose some models from those well-known models, or you build it yourself. Then you have a candidate model. Okay, you use the data to fit the model, but remember the model have a lot of hyperparameters to tune. Say, for example, if you want to build a linear model, how many predictors you want to choose. So linear model basically we are going to introduce later. It's a linear combination of all the input predictors. So how many predictors you want to choose, or whether you want to choose any intercept. Those are hyperparameters you want to tune. Okay, so one model is not enough. You need to do a model tuning. Okay, there are a lot of candidate models for you to choose from. You choose the best to deploy your golden model. This is the general process. And the golden model, after the golden model is built, you can do predictions with new raw data. Okay, so then that helps you to interact or to do any task or do any decision making. Okay. Then let's move to the each process. First of all, with the raw data, you have to do pre-process. So pre-process is a kind of you need to check and clean the data set. So most likely you will find, okay, this is a missing data, there are missing data, or there are outliers, or there are imbalanced data. Okay, by imbalance we mean sometimes maybe you collected one outcome too many. Say if you want to predict tomorrow whether it's going to rain or not, but you only collect the data that when it's raining. Okay, when tomorrow is not raining, you have not enough data to support it. So that in that case, your data set is so-called imbalanced. And also, we also do some feature engineering based on your knowledge about the problem you are trying to solve. Actually, as to do data science, it's not just about numbers. It's about your understanding of the problem. Okay, so the domain knowledge is also very important. The domain knowledge will help you to decide, okay, what kind of features are most relevant. Say if you want to predict the data raining, you probably have to search for the humidity of the weather, or whether there is a cold air coming or anything. Okay, so the better you understand the scenario, the better you can build a model. That's for sure. Okay, so feature engineering is based on your understanding of the problem. You do labeling or converting the data into your model input. Okay, including selection of the input features, extracting information, say the time, the day, time, hour of the day to make it the input. As I said, the input can only be numbers, so you extract those informations into numbers and get ready to build a model. Okay, so sometimes we have missing data. Say customers, they leave the survey questions blank. Okay, when they leave the survey, when you encounter this missing data, you need to know the categories. Maybe not applicable. Say because you have because you don't have a pet, you are asked the question about do you have a pet. Okay, you say no. Okay, or your pet name, you say no. Or unknown, meaning there is an answer but you didn't collect. Okay, maybe what's your age? So everybody should have this number, but you didn't collect. So this is missing by by another reason. Also, you forgot to type in accidentally deleted. Okay, because you need to understand the cause of the missing data in order to do imputations. Okay, maybe sometimes you can fill with 0. Usually it's this say pet name, not applicable. Not applicable, you can fill with 0, so that when others got a value, this one will indicate that, okay, this missing is because it's not applicable. Also, you can fill with mean, median, random, or KNN, which means K nearest neighbor. This is most dedicated model. This is some model that we use to fill in the missing value. Say, suppose I'm filling in the missing column, which is the age. Okay, then I will look into those rows that are similar. Look at those people that are similar to this guy, say occupations, working experience. Yeah, they are similar to this guy. What is the average of their age? This is so-called K nearest neighbor. Okay, so K nearest neighbor is a very commonly used technique to fill in to do missing data imputation. When we know that this feature should have a value, but we miss it. Okay. Also, we can do some time series filling. Say, since this data is a time series, from year 1 to year 2, there year 1 to year 1, year 2, year 3. You only have year 1 and year 3, but year 2 you can do some fill forward or fill backward with the data from year 1 and year 3. This is so-called time series filling. Okay. Yeah, this is part of scrapping data, or we call it data preprocessing. And also, one more important preprocessing is to drop the data. Okay, say suppose there are too much missing data, or suppose some features is really irrelevant. Say, for example, some IDs in the column that these IDs are generated only for identification. So there is no relation between the ID with the outcome. So you can safely remove IDs. But for the second one, I think for when missing data is too much, when you drop it, you have to be very careful because imputation first. If you really can't do imputation, you drop it because data collecting is expensive progress, but deleting is just a minute. Okay, so we have to make sure that every data we collect, we make full use of them. Okay, and also there is another category that is falling in the data preprocessing. Okay, until now we haven't gone into the real modeling part because data preprocess is something that is the most tedious part, and also there are a lot of cases that you have to make use of your understanding of the data to be able to preprocess it. Okay. Also, as a fact, I think most of people knows that for data scientists, so nowadays a lot of models have been built very well. You can use a lot of packages like scikit-learn or TensorFlow or PyTorch to build a lot of dedicated models, but these data changed depending on the problems. So nobody can give you a correct a definite answer saying that, okay, I have a very easy way to pre-process those data. So pre-processed data usually takes up 80% of the time for data scientists to build models. Okay, so building model part is just usually it's less than the pre-processing data, because data is a key, as I said, as we mentioned in the beginning of the this session. Okay, data is the key to generate a good model. Okay, for this category, for this kind of pre-process, it's not dealing with missing data, it's dealing with categorical data. Since data can be only numerical data can be fit into the model. So when we have categorical data, say like male, female, or membership tier, 3, Pro, Pro Plus, and Enterprise. So these are categorical. We say age groups or salary groups. So these categorical data, how can we convert them into numbers? So there is a way called one-hot encoding. Okay, one-hot encoding is to say, okay, before we talk about one-hot encoding, we have to decide one thing: is do we need one-hot encoding? Okay, because some categorical data, they have ordinal relationship in nature. Say months, January, February, March. You can represent them using 1, 2, 3, 4, 5 because they are ordinal in nature. Or you say the tier. Here, we can give a higher number, so they have an ordinal. But some of the data, they have no ordinal relationship. Say the brand of the cars. Do we have this kind of a Honda less than Toyota less than Benz? No, right? We can only say that whether it's Honda, whether it's Toyota. So these are Sunday, Monday, they have ordinal relationship. So we can do kind of ordinal encoding. But one-hot encoding is to do this kind of transformation. They create a lot of dummy columns. So say this car brand, they have Toyota, Humida, Honda, and Benz. They have 4 different categories. Then we create 4 different dummy columns. Okay. So each dummy column will contain whether the car is Toyota or not. So if it is, it's 1. If it is not, it's 0. So these 4 columns, you can imagine, it's going to be very, very sparse. That means a lot of zeros inside. Okay, only those car falling in one of the brand will be 1 for this this column. Okay. Okay. So far, I'll pause here for a little bit for you to digest what I have said so far. And later on, later on, we are going to start our journey on building a model. Okay. Okay. So far, I have 1 question. Oh no, not 1 question. Okay. So all the slides and the notebooks I'm going to use are going to be uploaded, so you don't have to worry. Also, I'm told that some of you might have not got your AWS Educate account approved, so don't worry about that. Probably today you won't be able to follow me with the operations on the AWS account, but you just take note what I have done. Later on, when you watch the video, you probably have got your account approved. Okay, so don't worry if your account is still not set up yet. So now let's start. Okay, with all the data being processed, we have already got a clean data set. There we are ready to build a model. So the model training part, model training and hyperparameter tuning is the part when you iteratively select a different set of parameters and build a model, choose the best one according to your evaluations metrics. Okay, and last step is to deploy a model. So after training the model, you need to save your model somewhere. You can save it locally using some Pico file. Okay, this Pico file will record all the details of your model. Also, you can choose to deploy to cloud. Okay, this is we are going to make use of AWS SageMaker later. Okay, to show you how to deploy to cloud. Then your model is served there. You can make predictions whenever you want to call. You can call the API to get the results you want. Okay. So today we are going to do an introduction. So I have chosen the most simple model, which is a linear model, to illustrate. Someone is turning on your mic, right? Anissa, could you turn off your mic? Hey, okay, yeah. So there are two examples I'm going to show. These two are both supervised learning. As I said, we are going to focus on supervised learning. So the first category is so-called regression. The second model is classification. So the difference between regression and classification is decided by the outcome you are trying to predict. Suppose if your outcome is a continuous and unbounded number, it will fall into the category of regression. If your outcome is discrete and finite choices, categorical outcome, then it's going to be a classification model. Okay, regression predicts for numbers. Those numbers can be anywhere, unbounded, from the minus infinity to infinity, and it's continuous. Okay, then classification is it's just finite choice. You try to predict which category it falls into. This is classification model. So for the first regression model, we are going to use linear regression. So linear regression is a basic supervised learning model. Although we are not going to use linear regression model directly in most of the cases. Linear regression is fundamental to many other larger models, say neural networks. So neural networks, you can imagine it is a collection of linear regression model, layer by layer. Okay, so I think next session about deep learning, you are going to touch this neural network models. And linear regression is easy to interpret and easy to solve. Otherwise, we have to spend the whole 2 hours to just train a model. Okay, linear regression is very easy to solve. So what is linear regression? I suppose you all know what is a Cartesian coordinate, right? So Cartesian coordinate is a coordinate that x represents here. X represents the input features. Y represents the outcome we are trying to predict. Okay, so each blue point is a data point. Okay, each data point we are supposed to build a linear model. So linear model assumes that x and y is a linear relationship. Okay, so we are supposed to build a model that will fit this data, and this model is in the form of y equals to beta 1 x plus beta 0. Beta 0 is the intercept, and plus the epsilon, which is a noise. So epsilon comes from the real data noise. the real data we collect, actually, if you are familiar with those Newton's experiment, they all assume that, okay, we are on absolutely no friction environment, or the environment is like a vacuum. Okay, so those experiments are ideal, but for in the reality, we all have uncertainties in the environment. So the data you collect is always variant. So this variance is due to the natural variance, and it's not avoidable. Okay, so there is no way to avoid this variance, this noise. Okay, so this noise that's why even if the underlying rule is a linear rule, we will see data collected being like this. They spread around this line. They are not absolute. They are not falling on the line perfectly. Okay. So this representation is a linear combination of input feature outcome equals to linear combination of input features, and the beta 0 is called the intercept. Okay. In other words, we say that target variable is only dependent on some linear combinations of the input variables, and this is called linear regression model. So we predict based on some error to modeling the problem, and the error is denoted by epsilon. As I said, this is not a void. This is not avoidable. Okay, and to build the line, actually we have a lot of choices. Okay, depending on the beta you choose and the intercept you choose, right? So you can choose a line like this, or choose a line like a horizontal line or vertical line, anything. But you need to choose a best fit line that will minimize the error. Okay, what is the error? The error is so-called, so error is the red bar. Okay, is the distance from the predicted value. So all the predicted values are on the line. Say, if it's 300, I predict the y should be 2 or 20. Okay, so if the y we collect from the data for 300 is not 20, then it's here. The difference is the red line. So we add all the red line, the value of the red line together. We get objective function, which is so-called mean square error. Okay, so the mean square error is the sum of the square error. The square error means y true value minus y predicted value. It will sum up together to get this is the measure of how good your model is doing, and this whole thing is called an objective function. An objective function is a guide for you to find the best fit line to those data. Okay, this objective function does not only apply to linear model; it applies to all the models, but in different format. For linear model, it's a quadratic equation. It's a quadratic function. Okay, you can see y equal y minus y predict square. So it's a quadratic function for objective function of a linear regression model, but it's in many other forms. But always, when you train a supervised learning model, you always have a prediction versus real value, actual value. So the difference between them is the how badly your model is doing, and you try to minimize the error between your predicted outcome and the true outcome. That's a rationale behind objective function. So objective function is used to guide your fit. Okay, to guide your fit and find the best fit model. And this solution is also called maximum likelihood estimator. Okay. Okay. That's the previous process is called fitting the data to the model to get the best fit. Okay. Then what we mean by best model is that this model also has a lot of, as I said, also has a lot of hyperparameters to tune, which is defined when you actually define the model, when you actually guess the model. So say, for example, if I want to build a linear model with y equals to a linear combination of x, then I need to choose how many x I want to put into the linear regression model. So how many x is a kind of hyperparameter. You first decide how many x you want to put into the model and what are the x you want to put. Then you do a fit. That objective function comes in to help you find the best coefficient that minimize your fit. Okay, don't confuse these two. So this hyperparameter tuning is to choose your best hyperparameter. Then the fit is to choose the best coefficient. Okay, in linear regression case, it's a coefficient. In other models, it could be other models parameters. Okay. Yeah. So this is the feature selection and model reduction. Later on, we'll use an example to illustrate. Okay. Then cross validation of the model means we want to later on we will talk about that. So usually when we do the selection of model, we don't do the model. We don't train and evaluate the model at the same time on the same data set, because that one will cause something called overfitting of the overfitting problem of the model. So we usually divide the data set into many smaller data sets and do training on one set of data and do validation on the other. So this kind of metric will be able to measure how good your model is, how predictive your model is. And these are different metrics we can choose from. Say mean square error, a root mean square error. Mean square error is just the square or sum of square over the number of data points. Okay, root mean square means square root of mean square error. Okay, and also R square. R square is also a metric that helps you to measure how far away is your predicted value from the true value. So this R square is a value between 0 to 1. And if it is close to 1, it means you are doing a good model. The model is a good fit to the data set. Okay, then adjusted R square is to take into account of the number of features you put in. So this K is the number of features you put in to the model. Okay, these are in general sense. You may have if you want to get the detailed definition and interpretation of these metrics, you may read more on linear regression theories. Okay, so this, okay, just to inform you that this is a very important concept in machine learning. It's called bias and variance. Just now I said that sometimes why we want to do some cross validation when we do a model selection, because if we measure the evaluation metric, say MSE, mean square error, on the training data set we have already done we are used on the training set that are used to train the model, we will encounter this kind of overfitting problem. So overfitting means if your means your model is doing very well on the training data set. Okay, I use a very complicated model to interpret every single data point in the training data set very well. But if my model is used to predict something that is outside your training data set, but from the same data source. Say same data source means suppose we are generating the weather record, okay? We generate for the same city and same time period. Okay? So these are from same data source, but different data sets. Okay, so probably this is the data, the first row of this data, the second row of this data. So different data sets from same data source. This model will have very large gap in the performance. That's so-called overfitting. Okay, so as the model gets more and more complicated, you can make your model more and more complicated by using, say, more features to predict, or by increasing the model's parameters. Okay, so say if you are using a tree model, that means you increase the size of the tree. Then for sure your bias, okay, your error between the model and your training data set is good, is small. But when you are testing your model on another data set, the model is not doing as well as the one on training data set. Okay, so this is so-called bias is a measure of your model error on the training data set. Okay, variance is a measure of your model on your model's predictive on another data set. Okay, so a truly performant model should seek a balance between the bias and variance. Okay, so it should do well on the observed data. So say you want to predict something according to historical data, right? You should be able to fit the historical data very well. Your model should be able to explain your history very well, but you should also do well on the unseen data, which is happen in the future. Okay, so so this is and also bias means error caused by simplifying the assumption. So model get simplified, will have more bias, and model get more complicated, will have higher variance. Okay, also there are irreducible errors. That is I have just said the epsilon, which is a noise that is unavoidable by nature. So we want to find a model that minimizes both bias and variance. And this is a graph that indicates how it changes. Okay, bias decreases as model complexity goes up. Okay, variance increases as model complexity goes up. So we want a model that is just at this point where they can have fairly low bias and variance. So bias and variance, we want to minimize them together. But actually they are inverse related. So increase bias means you probably have also decrease bias, you probably have increased your variance. So it's important to find a model that is at this point, you are able to minimize both. And to minimize both, first of all, you have to detect this kind of feature. You have to be able to evaluate both bias and variance. How to do that is to split the data. So splitting the data into a training set and testing set. Okay, suppose you have 1,000 points or 1,000 data points. You use, say, 80%, 800 data points as training data, and 200 points as your testing data. Okay, then you do a error metric. You calculate the error metric on the training data set. Will give you the bias of your model. So if your model fits the training data very well, gives you a very low value for MSE. Then if you test them on the training data set, you probably will find a huge gap between the MSE. Okay, then that will tells you, that will be a hint that probably your model is overfitting, or we say it's a high variance model. Okay, high variance is the same thing as a overfitting. Okay, so also testing on training data set is so-called in-sample test. Testing on some testing data set that you didn't use to train the model is called out of sample test. So the gap between in-sample and out of sample test is indicating the variance of your model, and the value for the in-sample test result is indicating your bias. So you want to try to minimize both bias and variance for this model. Okay, and that's enough. That's the whole cycle for building a linear regression model. Okay, you choose a linear regression, you select proper metrics, say mean square error or R square, to evaluate your linear regression model. Then you choose your best number of features and deploy your best linear regression model. That's enough for regression. Okay, and here as an illustration, I'm going to use a notebook, an example to illustrate how you build a linear regression in Python. And this IDE is Jupyter Lab. I think probably you have encountered, you are familiar with. So I'm not going to explain how to use Jupyter Lab. We'll go directly into the code. And this Jupyter Lab, okay, each cell, we can run it using Control plus Enter. So for here, we import the libraries we are going to import are going to be NumPy, okay, Matplotlib, Pandas, and Seaborn. Okay, these two are used to do plot. Okay, and also we are going to import this big library called scikit-learn. Okay, because scikit-learn is scikit-learn, you can refer to this this website. There are a lot of guides, and there are a lot of machine learning models you can choose from. Okay, this is the package of scikit-learn. You, if you want to do machine learning related work, you need to be familiar with this library, scikit-learn. Okay, then in scikit-learn there is a data set called load Boston. Okay, then this data set is when we load the Boston data set, they will tell you, okay, they will tell you this data set is indicating the Boston's house price from some criteria, say crime rate, okay, a zone, also the non-retail business area per town, and retail business per town, and also the age of the year of the house, and also some other indicators. Okay, so these are the features we are going to use to predict the outcome, which is the price. Okay, the outcome is a price, and the price should be a continuous number. Okay, so if we load the data frame and put them together, you can see each of them will be a number, a column of numbers, crime, zone, And the price, okay, price is here. This is the data frame of input features. So these are the input features we are going to use, and Y is going to be the target. Okay, so target is going to be our Y. And the first thing we need to do is to do the train test split, because we want to measure the variance, not only bias, but also variance. Okay, so always remember, before you do anything, okay, before you do anything to the data set, you first do a train test split, because you want to evaluate the variance properly. So this one, Boston split equals to train test split, and the train test split equals to the train test split is imported from also scikit-learn. Scikit-learn not only have models, they have the model selection to help you to select models. Also, they have a lot of pre-processed libraries you can use, you can choose from. Okay, these are some generators and pre-processed libraries, feature extractions. They are all quite useful. And this train test split is to split your data set. So this is telling you this is input X features we are going to use, and Y we are going to predict. And this is test size, means I'm using the 20% of the whole data set as my test size. Okay, and random state is a random number generator seed. Once you fix the random state, they will generate the same sequence of random numbers. Okay, so from the data frame, this pandas function called info, we can see that this data set does not have any missing value, and also all the data type are already float. That means this data set is cleaned up for you already. You are is ready to use. Okay, and the target is just one column, and also no missing value. It's a float. It's a continuous number we are trying to predict. And then we use some plot to see what's the distribution of the target value. Okay, so this is the distribution of the target value in training data set, and this is the distribution of target value in testing data set. Okay, so training data set, we want to make sure that training data set covers all the values, also as well as testing data set. Okay, this is you can see that it's a random, since they do it totally random. So you can see that also the distribution of the values are similar. Okay, so we go down, start to build our model. Okay, building the model. Before you build the model, you need to import. Okay, import the model. It's called linear regression from scikit-learn linear model. Okay, scikit-learn, there are a lot of models. You can choose linear models or tree models. You can import decision trees, random forests, and so on. Okay, and no matter what kind of model you import, okay, you always do these two. One is to, this first step is called so-called instantiation. Model instantiation is allows you to tell the computer, okay, I want to build a model that is linear regression because I assume the data is linearly related. Okay, I want to draw a line. Then the hyperparameters will tell you, okay, I want the intercept to be true. So So I will always have intercept. Okay. This is the first step. First step is to instantiate the model. Okay, tell the computer roughly what kind of model you are trying to build. And then second step is to fit. In fit, you fill in the training data set. Okay, training set X, training set Y. So the training set gives you, they use objective function, try to minimize the error between your predicted value and the training value. Also called minimize the MSE. Okay, so behind the fit function, you are actually using this data set to train the model. So the model will find the best fit to this training data set. And if you print out the linear regression coefficient, you will see it's a list of number. This number denotes your coefficient for each for each column. So first correspond to the prime, second correspond to the zone. Okay, you print out the coefficient and print out the intercept. Okay, so the intercept is 38, and that means even if your x is 0, okay, all your x are 0, your y is still 38. And you can store, so after you have built the model, you instantiate and fit. This model is built already. It's there already, ready to make any predictions. So if you put in test x, okay, linear regression model.predict, you put in x test, you will get the predicted price for those test data. Then you are able to measure all the metrics I have mentioned for the testing data set. Also, you can do this for training data set as well. Okay. Actually, they are the same. The function you use are the same. Metrics.Auc score is to calculate the Auc square, and the metric adjust the Auc square is calculated from Auc square using the definition. Okay, and MSE is also mean square error. RMSE is square root of mean square error. So they are calculated from the function or by the definition. Okay. Also, you can print out the in-sample metric. These are out-sample metric. You can calculate the in-sample metric using training Y. Okay, then training Y, training X. Also linear regression model dot predict X train. Okay, this is same training. Training. Oh, sorry. And by comparing the training data metric and the testing data metric, you can see that in general, training data metrics are always better than testing data metric because training data is already the best fit. Okay, you see, training is 0.7 something, but testing is 0.69. Okay, and also this part from scikit-learn feature selection. So now actually this model is built on the full model. It's built on all the 13 features. Okay, then we'll ask the question: can we drop some features? Okay, then you can use this kind of feature selection library called RFE. So you still build a linear regression model, but this time you do an RFE. And this 10 means I select only 10 features into my model. So they will select the most relevant 10 to your model, and you still fit it. Okay. This is still a linear model, but now since you are using RFE to restrict the number of features you fit in, they will iteratively do the selection and find the most correlated 10 features. Okay, and also if you plot, if you print out the support, you can see that there are 3 features that we didn't put in. Originally, we have 13 features, but only 10 features are put in. So these 3 features are age, text, and B. Okay, if we look at the description for these 3 features, okay, age is the building owner-occupied units prior to 1940, and B means is the proportion of Black people by town. Okay, so actually after the model selection thinks that these three features are most irrelevant, so they drop these 3. Okay. Yeah. So also you can plot out your line fitting the model. Okay. So the line looks like this, and your predicted x or your predicted y looks like this. Okay. So this is basically linear regression. We start with data set, okay, and instantiate the model, fit the model, predict the model, and evaluate using the matrix. And also, we do model reduction by selecting the top k features that we want to put in. In this way, we make the model less complicated. As I said, you adding more features means you make the complexity of the model higher. Then your variance is likely to go higher. If you can reduce your model, if you reduce the model by not affecting the bias very much, you probably can can find a better model that minimize bias and variance in the same time. Okay. There is a question from Cheng Yi saying, may I know if the feature selection from scikit-learn can also be used to select the features for other ML models such as classification? Yes, it can, because you see, the RFE is you just need to specify the number of you specify the model, then you specify the number of features you want to put in. Okay, so this one you can also do say logistic regression. Okay, you can also do that. But this applies to linear model. I'm not sure whether it applies to tree model as well, because in tree model you when you define the model, you already select the maximum feature you want to use. So for linear model, yes. For other models, I'm not sure. Okay. Yeah. So this is enough for regression problems. Then we are going to another very big category of machine learning problems, which is so-called classification. Okay. So classification is a discrete outcome, and you try to decide which category it falls into. And we are taking an example of binary value classification as an example. Multi-class, you can generalize later. We can see how it is generalized. So linear model. So for classification, we still assume behind underlying it's a linear relationship, but after linear model, we have to do some transformation. The transformation function is also called activation function. Okay, and this classification model we are using is called linear classification model. Also, it's called one of the linear classification model is called logistic regression. Okay, so here activation function is also very important concept because this activation function can transform the outcome of one model to another. This is particularly important when you do a complicated model like neural networks. When you have an output from the previous layer, the one layer will build a model. This model will will have a kind of output. Then you need to transform the output to some form that you are that is desired, then pass it to the next layer. So you need to be careful about this. Also pay attention to activation function. It will be used again and again in machine learning. So logistic regression is using this so-called sigmoid function. Okay, this sigmoid function, if you take a close look, so y predict of the logistic regression outcome is 1/1 plus e to the power of minus y. This y is a linear regression output. So linear regression output, if we remember, it is like this. It's a line. This line is from minus infinity to plus infinity. Okay, if you transform using this sigmoid function, okay, this sigmoid function looks like this. It falls between 0 and 1. And the good thing about this 0 and 1, we can link the outcome of outcome of a linear regression to a probability. So the probability is also 0 to 1 if you have some prior knowledge about statistics. Okay, probability means something happens. The chance of something happens. So if you roll a fair die, probability of getting 1 is 1/6. There are 6 different outcomes. If it's a fair roll, if you're rolling a die, the chance you get a particular number is 1/6. So this is the probability. And this here, the output of a linear regression is also a number between 0 to 1. So we can interpret this value as a probability of this outcome to be 1. So as it close to 1, it is 1. As it is close to 0, it is 0. So we can set a threshold, say 0.5. So greater than 50% chance, I say you are classified into 1. Less than 50% of chance, you are classified to 0. Okay. And this is also called an activation function called threshold activation. This is called a sigmoid activation function. Okay, sigmoid function, and both are activation function. So In order to do a classification from a linear model, we have to use two activation functions. One to transform from minus infinity to plus infinity to a continuous number between 0 and 1. Another is to transform a continuous number between 0 and 1 to a discrete choice of 0 and 1, binary choice. Okay, and how to evaluate classification model? We are going to use a completely different set of evaluation metrics, which is called, feature selection, and cross-validation also applies. As I said, cross-validation and feature selection not only applies to linear regression problem, also applies to classification problem. Okay, and the evaluation matrix is quite different. One is accuracy. One of them is accuracy. So accuracy is defined as the number of correct classification over the total number of classification. And AUC, which I'm going to talk about later, it's called the area on the curve. What kind of curve is it? What kind of curve it is? It's called ROC curve. Receiver of CE is I can't remember, but it's called ROC curve usually. It will be illustrated with examples. And confusion matrix. So confusion matrix for binary problem, usually 0 we call it negative, 1 we call it positive. So this confusion matrix, they have 4 entries to indicate different combinations of your predictions and actual what happened. So if it's actual negative and predicted you are predicted also negative, that means your prediction is correct for -1, for the negative data, then it's called true negative. If your predicted is positive and your actual is negative, then your prediction is wrong for this positive. Then you are, this is so-called false positive. And if your prediction is negative and actual is positive, that means your prediction on negative is false, so false negative. And true positive means your prediction on positive is correct. So these 4 numbers actually has indicated all the possible predictions you can make. Okay, right prediction on positive, wrong prediction on positive, right prediction on negative, and wrong prediction on negative. And the true positive rate is defined as the true positive over the total number of actual positive. So this true positive rate just means how many positive you have captured out of all the true positives, out of all the positive outcomes. And false positive rate is the number of false positive over all over true negative plus false positive. That means it's the number of all actual negative. So false positive rate means how many actually it is a -1. How many for those data that is actual negative, how many of them have been wrongly predicted as positive in your model? Okay, so if you plot a false positive rate versus a true positive rate, when you set the threshold, as I said, you need to set a threshold from, the threshold can be from 0 to 1, right? When you set the threshold from 0 to 1, you will get a curve. Okay, this curve is a false positive rate versus true positive rate, and the area under the curve is your AUC score. So AUC score is the most commonly used metric for evaluating classification problems, because this is the most general and accurate one. For accuracy, sometimes you have high accuracy, but you might not have a good AUC score. In the example we will see later. Okay, so AUC score is defined as an area under the curve. What kind of curve? It is ROC curve. ROC curve is a false positive rate versus true positive rate when your threshold is set from 0 to 1. Okay, if you set your threshold to be 0, you are going to predict everything to be positive. So that means both your true positive your true positive rate is going to be 1, and false positive rate also going to be 1. Okay, because everything is so this. If you set your threshold to be 0, okay, it's at this point, and as your threshold goes up, okay, goes to 1, means you predict everything to be negative. Then your false positive rate and the true positive rate are both 0. Okay, yeah, that's the explanation for AUC score, and that's the way you can evaluate your model. And how to do multi-class classification? Usually it's either it's 1 versus rest or 1 versus 1 method. Okay, either you say you have 3 different categories, then you do each one first. Okay, 0 versus non-zero, 1 versus non-ones, 2 versus non-twos. Then you compare them, you find the highest probability, which is the category you are going to fall into. Okay, and this is the I will then use another example, which is a classification problem using logistic regression. It's here, and this time our data set is about marketing result. Okay, this is called the direct marketing campaigns. So you receive a lot of probably have received a lot of calls to promote something for you, to see whether you want to subscribe or not. Okay, so this is the data set talking about that, and they are trying to predict whether the customer they call to is going to subscribe for this particular product or not. Okay, also as usual, our library used pandas and numpy and matplotlib. Also, you will see scikit-learn linear model. Now this time, instead of linear regression, we import logistic regression, as well as trend test split as usual, and Seaborn for plotting. Okay. Also, this time we also want to do some pre-processing from scikit-learn. So later on you will see how to apply the pre-processing library. And the data we are going to read from the CSV file here. Okay, and using data info, you can see no missing value. No missing value means we don't have to do imputations. But from the data type, we can see that this is the problem. Some of them are either int or float. Int or float, they are numbers. They can be directly used in the machine learning model. But objects are strings. As I said, day of week, okay, months, contact, loan, and education, especially, they are strings. They are categorical data. So categorical data cannot be applied directly in machine learning. So we have to convert the categorical data to a number. So let's first have a observe on the data shape. Okay, this data got 40,000, some 40,000 plus now data points and 21 columns. So that means there are 21 features for us to use. And we use data.head to observe what kind of data we can expect. So the month is as expected. It's August, November, and something. Housing, yes or no. So housing, we can convert to 1-0 binary value without a problem. But these education, say for example, education, there are unknowns. There are basic for 4 years, university degrees, all these. How can we convert them? Okay. Yeah, so as here we describe, okay, age is numeric, but all these are categorical. How can we convert the categorical data into numbers? So first of all, we use the unique function to get a sense how many categories are there in the education. Okay, so education, there are basic 4-year, basic 9-year, basic 6 years. So we can group them together and all call them all basic. This is to reduce the, remember the one hot encoding, the number of category, the more your categories you have, the more columns the more dummy columns you are going to create. So in order to avoid too many columns, that means your model is too complicated. We group some of the similar education level together, say basic, okay? Basic 9, basic 6, basic 4, they are all basic. And also, okay, data education now. After this transformation, we have successfully shortened the list of the category. And then we can observe doing some EDA, exploratory data analysis, to see, okay, how many outcomes we are expecting. So you can see that there is a huge imbalance in the outcome. 0 got 35,000. It's almost more than 80% of the data is 0. So most of people, they do not buy the product. They do no subscription. Only a few of them do the subscription. And if we group by, using group by, why, and calculate the mean for those numerical columns, this mean can only be applied to numerical columns. So you can see the age, okay, for 0 and 1, the age are similar. So it's hard to tell whether age is correlated to y, okay. Also, but duration, okay, duration is the time you call, okay. This number is quite different. And also, this can be an indicator that duration might affect the outcome a lot, since if you can call, if they talk for a long time, okay, the more likely they are going to subscribe. Okay. Yeah, this kind of group by and mean tells you how different it is for different categories. And then we can also group by jobs, okay, to explore what is the job categories that affects the y value, okay? Because y value, it seems to be quite different according to different jobs. Okay, also marital status. Okay, divorced, single, married, unknown. Okay, they have different Y values. And also education level. Yeah, we get some mean value to get a general sense how it's varying and how they are correlated with the outcome. Then these pandas, they got a plot function called crosstab. So you can do a stack bar. So this stack bar will be categorized. The different the different color will indicate different category, so different outcome. This orange indicates it's 1. 1 means subscribe. 0 means no. So if you plot the job, okay, the customer's job versus the probability of subscribing, you can see a huge variance. So if there is a huge variance on different categories of jobs, so that means job might have a big impact on the outcome of your direct marketing. Okay, then if you plot this marital status, okay, the difference in the successful direct marketing result rate is not changed very much. So it's hard to tell whether this is correlated or not. Also, for education level, you can see some categories, they have a higher successful rate. So probably this is correlated to the outcome. Okay. Similar for other categories, you can actually, so day of week, probably they have not many impact. But for the months of the year, it seems that the successful rate is much higher for December and March and October and September. So I'm not sure what happened to those months, but actually this is a hint that your outcome could be dependent on the months of the year. Okay. Also, you can plot age. Okay, the distribution of the age to see. Okay, what's the age distribution that you have your customer is in. Okay, after all the EDA, we have a generally have some sense on what are the features that are most likely related. Then we start by creating dummy columns for those categorical data. Okay, so this is using Pandas function called getDummy. Okay. Then if we plot, if we print out, let's explore the data dot shape again. Now, previously it was only 22 columns, correct? Previously it was only 22 columns, 21 columns. Now, after creating the dummy columns, we have already we created 72. Okay, we created 51 more columns. This is if you print out the column's name, you will see that okay, this is a implot. They created columns such as job student, job services, job self-employed. You see, they create a column's name depends on the job category. Yeah, job name. Okay, also similar for marital status. Okay, marital divorced, married, single, and unknown. Okay, in this case, you created you do one hot encoding for all of these categorical data, and your final column values. Okay. Also, there is one more thing you want to keep in mind. Okay, after you create all the dummy columns, you need to delete the original column because original column is still categorical, cannot be used. So you delete them, replace them by the dummy columns. So your final column value will be 62. And you use these 62 columns to create a logistic regression. As I said, this RFE can be applied to logistic regression as well. Okay. You select the top 18 features. Since now you have 62, if you put all 62 into your model not surely, but your model is having a high chance of getting overfitting problem. Because you are using too many features, you are making your model too complicated. So in this case, we do an RFE, select the top 18 columns. Still, we import the feature selection, we import logistic regression. Before you use RFE, you need to first instantiate your model. Tell the computer, now this time I'm going to use a logistic regression. Okay, then use RFE and select the top 18. And RFE.fit is these 18 features I want to fit with the data final. Okay. And now, okay. So now we have successfully built a logistic regression model with only 18 top features selected. Okay. But before that, you see we gone through all the tedious parts of exploring the categorical columns and do one hot encoding to that. Okay. Okay. This part is not used. So after the model fitting, we can do after the model fitting, we can predict using the X test. Okay. Oh, okay, sorry. So this one, as I said, before you do any logistic regression, you need to do a train test split. This is as usual. Okay, train test split 0.3. Now this time we use 30% as our training data testing data set, and 70% as training data set. Okay. So now this time we are not going to use RFE. Okay. We are using all the 62 features to build our logistic regression. We'll see how big its variance is. Okay, so let's say y predict equals to x test, and y predict train equals to log regression dot predict train. Okay. So accuracy of the classifier on test set is 0.9. That's surprising. That's surprisingly good. then we print on training set. A training set is X train, Y train, okay, 0.9. So it seems that our accuracy, okay, as I said, larger gap means you might have a larger variance, but it seems that we use all 62 features, we still get a very good model. Is it so? Let's look at the confusion matrix. Okay. Cross-validation. We don't do cross-validation first. We look at the confusion matrix. If you take a close look at the confusion matrix, actually, you predict the true. You predict the 0. So as we said, 0 has been. Sorry, I used the order 0, 1. So this is your true negative. This is your true positive. Remember this. The definition about confusion matrix. So confusion matrix. Okay. Confusion matrix is true negative, true positive, false positive, false negative. So this means I have predicted positive very well, 10,000, correct. But out of the negative part, I only predicted about 2/3. So I have 30% of chance predicted wrong negative one. Okay. If you look at this, I predicted positive correct. True positive is very huge, and the false positive is very slow, very low. So my precision, the positive I predict correct is the positive case I predict correct is of high chance, but the chance of predict the negative correct is lower. It's only around 60%. So that's why accuracy is not enough. So you only say accuracy is 0.9. Although accuracy is high, but it doesn't mean that you are predicting both positive and negative correct, because our data set is highly imbalanced. Okay. So the accuracy is here, and we try to calculate the ROC. Okay. Then the ROC shows a very bad result, which means 0.59. ROC is same as accuracy. It's between 0 and 1. So ROC value, it is 0.59. So what does that mean? That means actually your predictive, your prediction is not as good. It's because of the reason I have just stated. You predict positive case very well, but negative case not very well, because you have not you didn't consider the data set imbalance. Then what can we do with that? We can do something called oversampling. Okay, this is a technique that when your one of your category has much less data point as compared to the other, you can do something called oversampling. Okay, oversampling, we do same process as before, and we run all the cells. We just want to check out the result. Oh, I need to install this. Okay. Imbalance learn. Need to restart. Okay. While waiting for the results. Never mind. It's not a. I'm not sure what's the issue. I will solve this issue later. But if we do some kind of oversampling here, we'll be able to improve the ROC score. But this kind of imbalance will cause trouble for linear model. For other models, say like tree models, you actually can overcome this kind of problem. Okay, I think that's enough for the introduction to the linear model. Okay, then we will go to AWS SageMaker to introduce you to SageMaker. So SageMaker is a web service provided by AWS. I presume that you have already got your AWS account. You can log in, and there is a service called AWS SageMaker. If you don't have SageMaker in your dashboard, you can go to Service and search for SageMaker. Okay. You can go to Service and look into the SageMaker should be in machine learning. Okay, the first one. It's a fully managed machine learning environment for you. And in SageMaker, there are in the dashboard, actually you can see there are quite a number of things you can choose from. Okay. Okay. The question from Cheng Yi is, am I going to share the notebook and chat? Yeah, sure. I mean, the notebook is not going to share by the chat. It's going to be shared. It's going to be uploaded later on. I think Val is going to show you how to download it. Okay? I think you can download it from the website. Okay, we'll inform you later. Yeah, I think that's quite a lot because it's machine learning is a fairly big topic. Yeah, no problem. Machine learning is a fairly big topic, and I try to squeeze everything in just 2.5 hours. So, I mean, these are basic introductions to machine learning, and you just need to remember the big concepts like bias and variance for evaluating the model, and the objective function to fit the model, activation function to do transformations on the output, and all the supervised learning, unsupervised learning, those categories of we are going to demonstrate for that. You don't have to worry about that. Deploy the model is the last step. After you have done all the model selection, model training, model evaluation, model selection, and finally you need to deploy a model. So deploy the model, you need to go to the SageMaker. If you all can access your AWS account, you can do with me. If you don't, just follow my instructions. So SageMaker, there is a dashboard here. There is a panel here, and here you click the notebook. So SageMaker provides a similar similar IDEs to Jupyter Lab. Okay, everything you can use in Jupyter Lab, you can use in SageMaker notebook instance. Actually, I have created the instance. If you haven't, you can create notebook instance and give a name. Okay, you choose your instance type and create an IAM role for that for access. And finally, create notebook. This usually takes about 10 to 15 minutes. So I'm not going to create now. I'm going to use the one I have created. And when it's created, the status shows it's in service. Okay, the green little check. So in service, you have actions. Open Jupyter is Open Jupyter Notebook. Open Jupyter Lab is Open Jupyter Lab. Okay. So since I'm more familiar with Jupyter Lab, I'm going to open Jupyter Lab. And they are going to open this very similar to what I have here. This is my local Jupyter Lab. This is your SageMaker Jupyter Lab. Okay. So once we have started the Jupyter Lab environment, we can do everything we have done here. Okay. So actually, we can run all these locally, or we can run it here. The difference is, run it locally, it uses your own computing resource, your local CPU, your local RAM. If you use SageMaker Jupyter Lab, they will provide necessary. Actually, when you create the instance, they already ask you to specify this instance type. So this instance type is to specify the, say, CPU and RAM. So this MLT2 medium, you can have MLT2 large, which is faster, even faster, so extra large. So for our linear model, we just use the default one, which is the smallest. And also you can, so when you do, when you run any code on this SageMaker Jupyter Lab, they won't use any of your local computer resource. So you are able to play computer games when you are doing the training job. Okay, they won't affect each other. And also, they have the necessary packages installed for you. Okay, you can choose the environment they have specified for you. Say, for example, if you want to use PyTorch, you probably want to choose PyTorch images. Also, say, for example, TensorFlow, they have TensorFlow instances. So here we are going to use only Conda Python tree. They have all the scikit-learn packages installed. So here we are going to use back the same example, which is Boston dataset. Okay, all the previous steps, they are the same. Okay, load from the Boston, load the dataset, check the dataset, do some IDE, do some EDA, and as usual, we do a train test split. Okay, train test split. So now you have training dataset, training data features, training outcomes, and validation features, validation outcomes. Okay, so the validation and evaluation, they are actually the same, mentioning the same set, but validation is is the test set you use to do the model selection. So the whole process is like you split the data into training and validation set, training set, validation set. You do, you try one set of hyperparameter model on the training set and use the validation set to get the evaluation matrix. And you then in the next iteration, you just use another set of parameter, hyperparameter. Then you tune the model. You tune the model again with different settings on the training set. Fit on the training set again. Use the validation set to evaluate. Okay, so always they will give you a metric. But when the metric goes down, say the not goes down, when the metrics improved, you select the better model. So in this way, you can select the best model for your training. Okay, so now here is the difference. Okay, why do we bother to use Sagemaker to do the training? Because they can provide with a better CPU, larger RAM, as well as they can make use of those Amazon resources, say S3. Okay, so this time, actually previously we only we load the data from local. We have to save everything into a CSV and put it in the folder. We load from local, but here you can enjoy S3. Okay, you can put your data in S3, and they fetch the training data from S3 themselves, so you don't have to worry about the storage as well. So the storage, you can enjoy S3 unlimited storage. So here you need to first create a execution role. The troublesome thing about AWS is every time you create a resource, you have to get access. You have to set up an IAM role so that the IAM role have certain access to this resource. I think this one you have been told in the previous session. So for S3, okay, when you create this notebook, you have to make sure that you create a new role will have all the S3 access. Otherwise, you are not able to fetch the data from S3 buckets. Okay, then you need for this instance, for this particular job, I'm using S3 buckets, which is here. So the S3 bucket name is given by Sagemaker. Sagemaker will allocate a default bucket for you, so you can use that bucket, and you can use your customized prefix. So this prefix is more like a folder you create in the bucket. Okay. So you create your you specify the bucket, and this bucket is going to be here. You go to the service and S3. Okay, so S3 is okay. This is a list of all the buckets I have access to. Okay, so we go to this particular bucket, and this is the okay. This is actually the folder I have created. I created. Okay. Since I have run this job before, so I created this bucket, this particular folder in the bucket. Okay. And for Sagemaker, you need to write everything in S3. Okay. So for this time, since we have loaded, we have these 4 data sets for training, for validation, for training, for validation. And we are going to upload all the data sets into S3. And this function called SMAC, Sagemaker Amazon Common, is to write a NumPy array into a dense tensor, and encode into a binary IO, okay, a binary object. So the bottle tree is something. Bottle tree is a library in Python, helps you to manage the AWS resources. Okay, so you need to import bottle tree first. So the bottle tree, you need to create a session called S3 resource. So bottle tree session resource S3, and the bucket, you need to specify the bucket name. Object, you need to specify the path to your particular file. And finally, you upload the file object, which is a binary object, byte.io. Okay, it's a binary object. So SMAC helps you to write a NumPy array into a binary object. And this binary object is going to be uploaded to S3 through bottle tree. Okay, so this bottle tree will, okay, after uploading, they are saying uploading training data to location. So remember, this is your location. Okay. This is your location. So we go to this bucket first to see whether my file is there. SageMaker AP Southeast 1. Okay. So this is 2. So I need to go to 1. This one. Okay. And there is a SageMaker. Okay. Okay. Not SageMaker. My prefix is SageMaker demo. So according to this URL, you will be able to find your data loaded here. AP Southeast. This is US. Sorry. I need to. Yeah, this one. Okay, this one is the bucket SageMaker has created for me. It's a temporary bucket. And I will be able to upload my file into this. Okay. Okay, this is Elastic Beanstalk. SageMaker. Yeah, this is. Yeah. So demo and train. Okay. So you see your data is here. Your data is uploaded to this particular bucket and in this particular path. Okay. We successfully uploaded the training data. Also, we want to upload the validation data. Okay. The validation data also upload to the S3 bucket. Demo validation. Now the validation data is here. Okay. So now next is to specify the output location. Okay. So the output location is here. And whenever we have model trained out, we are going to save our model into a compressed file. Okay, we are going to write our model into a file and send to the output location. Okay, so these locations, they have already been specified and defined by S3, defined by SageMaker, and then it's easy to later on, if you want to deploy, they will, if you use deploy, they will directly go to this particular output file or output URL to get your model file and deploy it to the server. Okay, so now in order to train the train the model in SageMaker, it's a little bit different because SageMaker, they are not going to use directly the scikit-learn packages, but they have images. It's the concept of images. So it's not they install all the packages in the instances. They actually manage this in terms of a lot of containers. So So each container is called an image. So here, the container, if you say container get image URL, that means this image is saved somewhere. Okay, so this image is saved somewhere. If you want to, similar to import from scikit-learn, say import from scikit-learn is you find the location where your library is installed. But for AWS SageMaker, they find where the container, the image is stored, and they pull the image out from the container. Okay, then you need to specify. So they also have a library, which is a kind of wrapper, say SageMaker, called SageMaker. So you need to, in order to instantiate a linear model, you are not using, say, linear regression bracket. You are going to call this SageMaker wrapper, SageMaker estimator. So this SageMaker estimator will go to the container, and according to your role, this role is to provide you the access and training instance count. So how many instances you want to train on? This is depending on the computer power. Okay, so instance type, as we just seen, instance type can be large or medium or small. Okay, since our lab, Jupyter Lab is running on a small, but the training job is done in another instance. Instance you can imagine as a computer. Okay, this is a more powerful computer. Okay, so you can specify the instance type and also the output path. Okay, output path is defined in the previous cell. Okay, and SageMaker session is the session you define using SageMaker. They create a session in order to do all the jobs. Okay, so this time this linear model is not is now specified by this SageMaker function, but in fact it's pulling the linear learner. Okay, it's pulling the linear learner function, and also set parameter means how many features you want to select, and what kind of problem you are dealing with, what kind of model you are trying. Say linear learner and then regressor is a linear regression model. Okay, the minimum size batch is the size of the batch you send every time. Okay, so in this way, okay, this is a whole process you set up or you instantiate a model in SageMaker. Okay, it's different from local, but they are specifying similar things, except on AWS you need to specify your role to for access purpose, specify the computer power for where do you want to run the training job. Okay, and the output path, where do you want to save your model? Because everything is training online, they are not going to provide some. You are not going to be able to manage the storage like your local storage. So you can only specify an S3 storage, which is a permanent storage, to save your model. Okay, so saving this is to specify all the Amazon related properties like rows, containers, instance type, output path, sessions. This is special in SageMaker, Amazon SageMaker, and these hyperparameters are the hyperparameters you are using for your model. Okay, these are specifying the hyperparameters for models, similar as what we have specified, the number of features. You can also set, say, 11. Okay, they will select 11 features for you. Now it's 13 features. and the predictor type is regressor. Regressor means it's a linear regression model. Okay, then after specifying those model related as well as AWS related properties, we are able to fit. But this kind of fit is different in the sense that you can specify your training data position and validation data position. So this fit is no longer doing in your local memory. So previously, this fit is fitting the data set you have created in your memory. Now in SageMaker, the fit is created on Amazon. Okay, so on Amazon, they have to know where to fetch the training data set and where to fetch the validation data set. So they get both data sets from S3 to fit your linear model. So in this way, your linear model is trained. Okay, and this takes much longer than you do it in local. You remember in local it's just less than a second. Your linear model is trained. This one they have to initialize a lot of resources, but the good thing is you don't have to worry about the resources. They will manage for you. You can when they are doing the training job, you just go and play your game. Okay. Then after the model is trained, this deploy command linear.deploy is for you to deploy the model. Okay, the deploy means you save the model you register the model in some server. So this server will always up there for you to use. Okay, so when we are doing the training job, let's go back to the SageMaker. This is Amazon S3. Let's go. Hey, someone is talking. Okay.
Don't know lah. I don't care.
Hmm.
Also not the one watching.
Okay. So while we are doing the training job, we can see this in the processing. Okay. So the processing job is here. So in progress is the status. That means this is the job we are running, and this is the job name. Okay. And the creation time, duration, and the ARN. And the training, actually we can have a look at the model. Okay, the model is still not yet because the training job is not finished. Okay. Once
inside your own bedroom. I didn't bring it inside one hall. How to watch TV from inside?
Sorry, Tom R. You are not muted. Okay. So that's something different in Amazon Web Service. Okay. Everything you need to do to deal with the access, images, and locations. Okay, you need to specify your storage, your access role, and the image you are going to use. So this image you can think of as a container that contains the necessary packages you need. Okay, so as long as you pull the image out, you are able to use all the packages inside. So this is the training job. Downloading, inputting data. Okay, they are still, you see, they haven't yet download the inputting data. They launch the requested, launch the job first, then they do all the things. Okay, approach. they do all the things. So you can see it takes a long time. And finally, once we finish the training, okay, the training job completed. Okay, training job completed. The next step is to use SageMaker to deploy. Okay, linear.deploy. So this linear is not a scikit-learn model. It's a SageMaker model. So this model contains some more functions than scikit-learn, because this model is built by SageMaker wrapper. Okay, so they can do directly deploy to some instance. So you can deploy on one instance, multiple instances. Okay, one instance. Sometimes if you're making some server that is quite busy, say for example our Grab booking service, they might need more than just one instance. They might need not just an instance, but a scaling group. They can auto scale to a larger group, to a larger amount, and also the size should be large. Okay. So the deploy also takes time, but since the model is done, let's look at the status of our model. You see, now the model appears in the model in the interface. Sorry, the model appears in the inference. Okay. Previously, when we click the model, there is nothing here. Now the model appears. It's called linear learner. This is the name of our model, and the endpoint. Okay, you can see that the endpoint is creating. The status is creating. That means we are still deploying this endpoint. Okay, it's deployed on one instance with this type. Okay, and the serializer, deserializer means it's an encoder and decoder. Okay. So now, once this deployment done, we are able to call this endpoint. Okay, so this endpoint is there, and we are able to call the endpoint from its name, which is here in this code. Okay, this is to show you a call inside the memory, but this part to invoke the endpoint to do predictions. So first of all, you need to be able to write your CSV file into a byte, into a binary object. Okay. Then invoke the endpoint. So this is your endpoint name, and content type payload. So payload is going to be a transformed data from test X, and we are let's see, the deployment is still ongoing. Okay, when the deployment is completed, the status is going to be changed. So up until now, we are able to. So until now, we have learned how to create a model on AWS SageMaker, as well as is there a GPU intensive task? Say pre-training. Can I do it? Yeah, there is GPUs in there is a GPU intensive task like TensorFlow training. You can specify. You see, that's why you are allowed to specify the instance when you are doing the training. So this instance is CPU intensive. You can also have instances that is GPU intensive. So you specify the type and specify the number of instances you want to use if it's a GPU intensive task. Okay, They also here, let me check. Yeah, so in AWS, you can specify all kinds of resources you can think of, from storage to memory to computer power to GPU. Okay, all these you can specify when you do the training job specification. So when you create the job, when you create the model, so now it's a linear model. You can use also a TensorFlow image. Okay, you create a TensorFlow model, but this model is AWS SageMaker also write a wrapper around it. So they inherited all the hyperparameters you can tune for this model in say scikit-learn or TensorFlow. Also, they have additional properties help you to manage those AWS resources, like access, like instances, like storage. Okay. Okay, I think our job is our job training is done, right? It's still okay. One more. Our job training is almost done. Okay. So while we are doing the job training, do we have any questions? And also, I have put all the. There are several examples that you can learn from the Amazon's GitHub Lab. This is some examples that are created by this guy, and also this is an example created by Amazon for you to learn how to use SageMaker. There are quite a number of examples and well documented. Actually, you are not just able to, you're not only confined to do model training and deployment, you can also do auto tuning, okay, automatic model tuning. They'll show the examples, and also there are various packages you can use, say XGBoost, TensorFlow, Keras, also neural topics. Yeah, a lot of things you can do with AWS SageMaker. Okay. Once your account is approved, you should be able to try all of them. Okay. Yeah. So if they show this, that means your deployment is done, and you can see in service. Okay, that means this endpoint is in service, and with then you can forget all about all the previous work you have done. Now what you need to do is just to specify a payload, specify the features that you want to predict. Okay, then send to AWS to this SageMaker runtime, SageMaker endpoint. Okay, so also bottle tree. You see, bottle tree is a very useful library for you to manage the resources. So client would be bottle tree client SageMaker runtime. Okay, then you specify the endpoint name, which is the most important, and specify the payload. So payload is a binary object that is created from the test data, okay, the test X, and you can see it's you call this endpoint through an HTTP call, okay. Then the response is get from this endpoint, and the response is a JSON file. The body is also, you see, the body is also a binary object. So you need to decode them. Okay, you need to decode from the body value, and you are able to get your final predictor results. So these are the corresponding predicted results from your test X. Okay, so test X. Finally, if you don't want, since this kind of service is a paid service, you have to pay money for that. So if you don't want to use it, better delete it. Okay, you delete the endpoint. Okay, delete the endpoint. Then the endpoint is gone. You refresh, you will see the endpoint is gone. Okay, empty. Now you can't see any endpoint, but actually in your inference, you still can find the model. Okay, if you want to reuse the model, it's still possible. Okay, you just need to deploy the model again. So far, any questions? How to deploy the pre-trained model on a website, for example, using SageMaker? Yes, this is okay. You can refer to this example, which is quite. That's why I recommend you to look at this. Okay, SageMaker, they have a very well documented GitHub repo to teach you how to use SageMaker to deploy your trained model. Okay, there is a SageMaker auto algorithms. SageMaker RL. You can find examples here. Actually, the general process is you remember your model. When you train the model, you actually save your model into a file that is okay. Let's go back to the S3. In S3, you will see a model that is saved in the output file directory. Okay, this one. In this directory. Output, there is this, okay. There is this model.tar file. This is this is a compressed file containing the model file. Okay, actually, after you actually all the saving model techniques, they are the same. They write the model into a model file. Either it's a pickle file or a model file defined by the particular package. Say TensorFlow is a TF file. So all the files, they are just files, right? You save the files and follow the instructions in the. Let me check if there is a example. SageMaker. There should be an example here. Sorry. Oh, here. Introduction to custom. If you there is a let me check. In the documentation, there is also documents for you to check how to deploy the model. How to deploy the model, how to deploy a pre-trained model deployment. Okay, you may follow their examples and create model API, invoke. Yeah, actually, this introduction is just to introduce you one of the ways to use SageMaker. is to use SageMaker. This is so-called SageMaker. This is so-called SageMaker default images, right? You can put your model together with the packages and push a Docker, push an image to make your own customized image. Amazon SageMaker. Oh, this is hyperparameter tuning. SageMaker feature store. Can't remember where the example is. But actually, there is a bring your own model. You see this example. See, create resource needed for activate. So use your own notebook. Use this notebook. You need to do something to check. Okay, check the file, your input files, and so on. And you push your model into an image. You need to follow the steps to trigger the activate. Bring your own model. You see, use the part of the code to learn. Actually, you need to use another resource called Amazon Elastic Container Registry. Okay, you register your model together with the packages as a new container, as a new image, and then you pull that image and deploy it. This is a fairly more complicated process. So actually, I should say Amazon SageMaker has already got all the possible libraries that you can use. Okay, so you don't have to do a pre-training. You can use Amazon SageMaker to do the model training for you, and that deployment is easier. If you want to deploy a pre-trained model, it's more complicated. You have to create a new Docker image. See, print the image name in ECR. Yeah. This is very complicated and tedious. Any? Okay. Actually, this after this session, you have 2 more sessions about SageMaker. You can also check with the next instructor. In fact, for this, have you seen this GitHub documentation? Actually, this GitHub, they have given you this instructions on training on how to Dockerize your own model image and do the training. Okay, this session is introduction. Don't worry, you will be able to solve this probably in the next few sessions. Okay. Yeah, it's not a deploy using SageMaker. Yeah, as I said, you see, SageMaker, you can after you have registered your own model as a Docker image, you can specify the container here. in SageMaker. Okay, since this is a linear, right? Linear model you are training the linear model using this one, using this estimator.estimator, then container, right? This container is actually the linear container. It's a base image. Then you, if you can register your model with a new customized ECR, customized image, you are able to specify the new image, which is specified here. New classifier. New classifier, then everything follows the same step. Deploy using SageMaker. Okay, I think this one you may check with next instructor. Also, any other questions? Actually, I haven't done this before. In Lambda function, I can use an API to trigger the model. Okay. To be used on Lambda function. For deep learning, the TensorFlow is very big to use. Yeah, that's why I said for TensorFlow, you can use TensorFlow image to train your model. But if you have your model ready, okay, you do you really need to deploy your pre-trained model, or do you have if you have the data and you can use TensorFlow on SageMaker to do the training and deployment, as I have shown here, right? Actually, Lambda function is not how to say, Lambda function is not an API. A Lambda function is a function that helps you to call this SageMaker model serving. Yeah, okay. To load the libraries. Yeah. Okay. I'll pass to Val. Val will give you some instructions on how to download the notebooks and slides.
Yeah, I guess that's the end of the session, everyone. I will get the notebooks and slides from Soon Chang, and then I will upload it onto the website. So if let's say you have like more